X-ray diffraction or XRD is a non-destructive technique used to study the crystal structure of crystalline materials. It helps scientists understand how atoms are arranged inside a crystal without damaging the sample. Because of this, XRD is widely used in physics, chemistry, material science, and engineering. One of the earliest XRD technique is the Laue method, introduced by the German physicist Max Volue in 1912. His discovery showed that X-ray can be diffracted by crystal, which became the foundation of modern X-ray crystallography. This important discovery helped scientists understand crystal structure better and earned Max Volue the Nobel Prize in Physics in 1940. The Laue method works by shining a white or polychromatic X-ray beam onto a stationary single crystal. When the X-ray interact with the crystal, they produce a unique diffraction pattern called the Laue pattern. By studying this pattern, scientists can determine the crystal orientation, identify its symmetry, and check its quality. This information is very important for research and industrial application. Even though the Laue method was developed over 100 years ago, it is still widely used today. It is important in crystallography, semiconductor manufacturing, material science, and synchrotron research because it is a fast, accurate, and non-destructive way to study single crystal. For this presentation, the information was collected through a literal review using reliable academic sources such as scientific journal, research article, and lecture notes. These sources were carefully reviewed to make sure the information is accurate, trustworthy, and relevant to modern physics.
The Laue method in X-ray diffraction works by using a polychromatic or white X-ray beam containing multiple wavelengths while the crystal remains stationary during the experiment. Different wavelengths satisfy Bragg's law simultaneously, causing multiple crystal planes to diffract at the same time and producing multiple diffraction spots in a single exposure. This enables rapid data collection without rotating the sample. However, the Laue method also faces several challenges. The wavelength of each diffraction peak is unknown, making pattern indexing and analysis more difficult. Diffraction peaks can also overlap, which complicates data interpretation. In addition, accurate measurement require high-intensity synchrotron sources, precise beam focusing, and advanced equipment.
The first importance of the Laue method is to determining crystal orientation. By analyzing the diffraction pattern produced when X-ray pass through a single crystal, scientists can accurately identify crystal orientation. This is especially important before cutting or processing crystal for scientific experiment, semiconductor device, and optical components because the crystal orientation directly affects their performance. Another important application of the Laue method is to analyzing crystal symmetry. The diffraction pattern reflects the internal arrangement of atoms and allow researchers to determine the crystal symmetry, also known as the Laue group. This information helps classify crystals into different crystal systems and provide insight into their structural properties. The Laue method is an important tool in material science research. It helps scientists study the crystal structure of metals, alloys, ceramic, and advanced materials. Researchers can observe crystal growth, phase transformation, deformation, and internal stress, which help them develop stronger and more durable materials. Modern research on advanced materials also relies on the Laue method. It is used to investigate superconductors, ferroelectric materials, piezoelectric crystals, and nanomaterials. By understanding crystal orientation and strain, researchers can optimize the properties of these materials for use in electronic energy storage and medical technologies.
I will explain the experimental setup of the Laue method. First, a polychromatic or white X-ray source is used because it contains many different wavelengths. The X-ray then passes through a collimator, which narrows the beam so it is more focused before reaching the crystal. Next, the beam is directed into a stationary single crystal specimen. Unlike some other X-ray diffraction method, the crystal does not need to rotate during the experiment. Finally, the diffracted X-rays are recorded by a flat film or detector, which can be placed either behind the crystal for transmission geometry or in front of the crystal for back reflection geometry. The recorded pattern is then used for crystal analysis. Next is the working principle of the Laue method. The process begins by generating polychromatic X-ray, which are directed into a fixed crystal. Since the X-ray contain multiple wavelengths, different set of crystal planes satisfy Bragg's condition at the same time. As a result, the crystal diffract different wavelengths in different directions. These diffracted planes are then detected by the detector or film, producing a unique Laue spot pattern. This spot pattern provides information about the crystal orientation. An important advantage of this method is that the crystal remains stationary throughout the experiment, so no rotation is required. The physics behind the Laue method is based on Bragg's law, which is written as n lambda equals to 2d sin theta. In this equation, n is order of diffraction, lambda is the wavelength of X-ray, d is distance between crystal planes, and theta is the Bragg's angle. Bragg's law explains the condition for constructive interference, where strong diffraction occurs. It also relates the crystal structure to the diffraction pattern. Because the Laue method uses many wavelengths at once, different crystal planes satisfy Bragg's law simultaneously, producing the characteristic spot patterns. This makes it possible to determine the orientation of the crystal accurately.
Next, I will explain some important implications of X-ray diffraction. First, X-ray diffraction is used to determine the crystallographic orientation of single crystal material. This helps researchers understand how crystal is aligned and structured. Secondly, X-ray map the zone axis and reveals symmetry and arrangement of atoms within a crystal lattice. This information is important for studying material properties and crystal structure. Lastly, X-ray diffraction can be used to analyze protein and biological macromolecules rapidly before significant radiation damage occurs. Now, let's look at some recent advancements in X-ray diffraction technology. The first advancement is the use of synchrotron radiation source. This source produces extremely bright and instant X-ray beam, resulting in sharper and more accurate diffraction pattern. The second advancement is the developing of in situ and operador studies. This allows crystal to be examined under real operating conditions instead of isolated laboratory, providing more realistic results. And another important advancement is time-resolved low diffraction. By combining fast-pulse synchrotron beam with optical pumping technique, scientists can observe atomic structural changes in real time on extremely short time scale, from picoseconds to femtoseconds. These advancements have greatly improved accuracy, speed, and capability of X-ray.
Now, I will present the final section of our presentation, which focus on the career opportunity related to the Laue method and X-ray diffraction. The Laue method is widely used in scientific research and many high-technology industry, creating various career opportunities. One example is crystallographer, who studies the arrangement of atoms in crystal using X-ray diffraction techniques. This helps scientists understand the structure and properties of different materials. Another career is a material scientist. Material scientists develop and improve material used in products such as aircraft components, medical implants, batteries, and electronic devices. They use techniques like the Laue method to analyze crystal structure and ensure the material have the required properties. The Laue method is also important in the semiconductor industry. Semiconductor engineers use crystal orientation techniques to manufacture silicon wafers, which are essential for producing computer chips, smartphones, and other electronic devices. In research laboratories, X-ray diffraction specialists and physicists use this technique to study new material, identify crystal defects, and support scientific discoveries. To succeed in these careers, several important skills are required. First, a strong understanding of physics and mathematics is essential because this subject explains how X-rays interact with crystal structure. Next is problem solving. sample often have a complex, high-density spot pattern, so it is important to possess the patience and resourcefulness to iterate through index fittings and troubleshoot alignment issue. In addition, professionals also must pay meticulous attention to detail. Working with small single crystals require extreme precision, and angular misorientation of even a fraction of a degree can ruin expensive materials. Other skills that are required in this field is pattern indexing and software proficiency. Modern Laue methods rely heavily on digital camera and specialized crystallography software. Professionals must be comfortable simulating patterns, interpreting indexing results, and calculating misorientation. Lastly, professionals also need computer and data analysis skills to interpret diffraction pattern using specialized software. In conclusion, the Laue method is an important X-ray diffraction technique that uses white X-rays and a stationary crystal to determine crystal orientation and analyze crystal structure. It has many applications in research, material science, and the semiconductor industry, making it an essential tool in modern physics. Furthermore, it offers exciting career opportunities for those interested in scientific research and technological innovation.